Yes, you are audible.
Okay.
And now we can start. So, good evening to all. And actually, Dr. Aparajeo Chattopadhyay, I cannot put my camera on because there is no camera in my desktop. So, Mr. Aparajeo is Dr. Aparajeo Chattopadhyay is one of my batchmate in the Calcutta University when we were studying MSc in Rajabaraja Science College. So I am fortunate to have him here within us. And I would like to request Nilmadhav Mukherjee, one of the research scholar in the Department of Industrial and Applied Chemistry, to just give the introduction.
Am I audible, Maharaj?
Yes, yes.
Okay. Janoning Sharodang Deving Ramakrishnam Jagadgurum Padapatme Tayo Sritya Pranamami Muhurmuhu. Respected Principal Maharaj Swami Mahaprabhananda Maharaj, respected Coordinator Maharaj Swami Indashanandaji Maharaj, revered monastic members of Ramakrishna Mission Vidya Mandira Belur Mott, and esteemed faculty, dear fellow students and others. Good evening to all, and good morning to Dr. Aparajeo Chattopadhyay sir. It is my privilege and honor to welcome you all to today's seminar on atmospheric chemistry of greenhouse gases. We are especially honored to have with us Dr. Aparajeo Chattopadhyay, a scientist in the Petrenko Lab at the University of Rochester. His research focuses on the intricate chemistry of our atmosphere, addressing critical issues in air quality and climate change. His specific interests include the global methane budget, hydroxyl radical abundance in both past and present atmospheres, gas kinetics, photochemistry, spectroscopy, ice core studies, and atmospheric monitoring. Before joining the University of Rochester, Dr. Chattopadhyay served as a research scientist at the NOAA Chemical Science Laboratory and the Cooperative Institute for Research in Environmental Science, University of Colorado, Boulder, from 2018 to 2023. He received his PhD in physical chemistry from the Indian Association for the Cultivation of Science in 2018. His outstanding contributions to science have been recognized with several prestigious honors, including the Researcher Development Grant 2022 from the Royal Society of Chemistry, UK, the Newton International Fellowship Award 2018, jointly from the Royal Society UK and ACRB India, the International Travel Grant from the Government of India, and two Best Poster Presentation Awards at the National Symposium on Radiation and Photochemistry in 2013 and 2015. Dr. Chattopadhyay is an active member of leading scientific organizations, including the American Geophysical Union and the Royal Society of Chemistry, reflecting his commitment to advancing global research collaboration. In the esteemed presence of revered Principal Maharaj and Swami Indreshanandaji Maharaj, it is indeed a privilege to welcome such an accomplished scientist whose work breeds rigorous research and environmental responsibility. Without further delay, I humbly invite Dr. Aparajeo Chattopadhyay sir to deliver his talk. Thank you.
Um, Thank you for your kind introduction. Okay, yeah, thank you very much for inviting me. I have given a presentation few years back in one of the seminars organized by Ramakrishna Mission. So it's indeed a great pleasure, and I'm excited to see a lot of students. Yeah, I'll be talking about atmospheric chemistry of greenhouse gases. I was told, and I can see there are a lot of students, so I would like to keep it as descriptive as possible. Don't want to uh, use too many research terms so that it is understandable to everybody. Uh, Here is a little bit of my background. I did my undergraduate and postgraduate studies from the University of Calcutta. In particular, I did my BSc from the Sipur, Dinabandhu Institution College, and then my MSc from the Rajabhajar Science College. Yeah, so and then I did my PhD from the Indian Association for the Cultivation of Science. and worked at NOAA and currently at University of Rochester. So here is the outline of my talk. I'll talk about my research interest. I'll go through some basics of atmospheric chemistry. I think it is not yet a regular subject in our bachelor's or master's curriculum. So I'll give some basics. In particular, I'll talk about climate and greenhouse gases. Then regarding my research work, I'll present my selected work from NOAA, particularly on the atmospheric chemistry of halogenated gases. And then I'll talk about my a glimpse of my current and future research at the University of Rochester um in atmospheric chemistry of methane. Okay, so let's talk about our atmosphere. This is an image of our atmosphere, Earth's atmosphere. This image was taken from the International Space Station. This is the air glow that makes our different layers of our atmosphere visible. Uh, so our atmosphere is like uh, we call it skin of an apple. It's very thin, but yet a very important blanket. It acts as a blanket to protect our planet from harmful radiation from sunlight, and also helps to maintain our Earth's temperature. So it's very important. If we look at Earth, the diameter of our planet is about 12,000 kilometers. On the other hand, the atmosphere extends to only 50 to 100 kilometers. So it's very thin. And here are some of the here are the layers of the atmosphere, and the layers are actually the layers are based on the temperature. The lowermost atmosphere is the troposphere, where we live. As you go a height in altitude, the temperature goes down. Then there is stratosphere. In here, the temperature goes up with altitude. Stratosphere also is home for the ozone layer, the famous ozone layer that protects our planet from the harmful ultraviolet radiation of sunlight. And there are some upper atmospheres, but mainly the most of the mass of atmosphere is within this troposphere and stratosphere. Okay, so now let's talk about atmospheric chemistry. What is atmospheric chemistry? It is the study of the chemical and physical processes that affect the chemical composition of the atmosphere. So what is the chemical composition of the atmosphere? I think most of you know that atmosphere is composed of mainly nitrogen and oxygen gases, a little bit of argon, and all other gases combined are only 0.1%. And they are known as trace gases because of this extremely low abundance. But these trace gases are responsible for major atmospheric events. For example, carbon dioxide, methane, and other greenhouse gases are responsible for climate change. Uh, Gases like ozone, nitrogen oxides, volatile organic compounds are responsible for air pollution. Volatile organic compounds are, in short, we call VOCs. These are compounds, organic compounds which are volatile. For example, some common examples are acetone, methanol, some of the chemicals that you use regularly. Also, hydrocarbons. They're very important for air pollution. And there are other compounds which are also kind of VOCs, like halogenated compounds, chlorofluorocarbons, etc. They are responsible for ozone layer depletion. So this only 0.1% of the constituent gases, they are actually responsible for the major events that happen in the atmosphere. And we'll see some of the examples. Here is the structure of the atmospheric chemistry research. We can divide it we can think it as a three-leg stool, where the components of the stool are field studies, laboratory studies, and atmospheric modeling. In field studies, we measure these different atmospheric chemicals using either from aircraft campaign or balloons or just field campaign, from satellite also. And the laboratory studies is where we measure or study the chemistry of these components. And atmospheric modeling is that we want to model and understand what we are observing is in the field, whether it makes sense or not based on the chemistry. So laboratory study actually bridge between field studies and atmospheric modeling. Okay, so these are fundamental sciences that we apply in societal issues such as air quality, climate, and ozone. Um, Now, one thing I want to mention here is that atmospheric chemistry is a very multidisciplinary research field. We have contributions from chemists, physicists, and engineers. So anybody can basically come to this field and contribute. Okay, now let's look in more details about the atmospheric processes. We can divide our planet in different boxes like this, both horizontally and vertically. Let's take one of these boxes. Let's take it here. So as I said, our main objective here is to understand the factor that is affecting the abundance of an atmospheric chemical. And let's take an example of a VOC that I just said, VOC, the volatile organic compound. So we want to understand in this atmospheric box, what are the factors that affect the abundance of this VOC? So it is guided by mainly two terms. One is the sources and the sinks. The sources are mainly emission from different sources. There are also chemical production, chemical reactions that is generating this VOC. And the losses are chemical loss, that is by chemical reaction, or deposition to the surface, or to clouds, maybe rains. So these are the different factors that control or determine the concentration of a VOC in this box. And there are several other boxes. So there will be transport. There will be air flowing from one box to the other, and from this box to the other box. So this is meteorology. So you also take into account of that. But what I want to learn, want you to learn from this particular slide is that the basic takeaway is different sources and sinks determine the atmospheric abundance of a VOC. And we want to understand these sources and sinks. So let's look at what are the sources, particularly the emissions. So the emission of VOCs could be either from natural sources, such as biogenic emission, biomass burning, volcanic eruptions, or by anthropogenic sources. Anthro means man, so man-made, whatever is not natural, whatever we are doing, the man-made sources such as industrial sources, cooking fire, or vehicular sources, which is basically fossil source. So after being emitted into the atmosphere, these VOCs undergo chemistry or chemical transformation, and our atmosphere has a oxidative behavior. So it's an oxidizing environment. So they are being oxidized mainly by hydroxyl radical or OH. OH is the primary atmospheric oxidant. It reacts with almost all of the VOCs and other chemicals that are in the atmosphere. For that reason, it is also called the atmospheric detergent. It helps us cleaning the atmosphere from this bad pollutants and other compounds. So hydroxyl radical in the atmosphere is actually produced by photochemistry of ozone. In presence of sunlight, ozone dissociates to produce O singlet D, which reacts with water vapor to produce hydroxyl radicals. So these hydroxyl radicals react with VOC and in this reaction, other organic radicals are being formed. As you know, radicals are not stable species. They instantaneously react with other chemicals and form stable end products. But what we want to understand here is that what is the rate of this reaction? This is important here because this determines the atmospheric lifetime. If the rate is really fast, then that chemical will not survive long in the atmosphere. If the rate is slow, then it will survive for long. And this atmospheric lifetime can be it's in the range of few hours to thousands of years, and that is really important. How long a chemical is surviving in the atmosphere, and that determines a lot of important atmospheric phenomena. So this is the formula that we use to determine atmospheric lifetime. We need the rate constant and the concentration of OH, which is known. OH concentration is pretty low. It's about 10 to the power 6 molecules per cc. Uh, there are other oxidants as well. OH is the main oxidant, but there is a chlorine atom, which is particularly important in coastal region. There is nitride radical, which is important particularly for the nighttime chemistry. Ozone itself is a oxidant. O singlet D, mainly in the stratosphere, and of course direct photodissociation. So atmospheric oxidation chemistry has a critical impact on major atmospheric events such as climate change, air quality, and ozone layer depletion, as I said. Okay, we will be focusing today mainly on the climate. So let's look at Earth's energy balance. Here are the black body curves for radiation coming from sun. You can think or consider sun as a black body, and I think some of you who know the introduction of quantum mechanics know that this black body radiation curve was explained by Max Planck, and it was a revolutionary invention that energy can only be received or emitted by packets in energy h nu, and the how much what wavelength black body is emitting is related to its temperature. Sun's temperature is really high, about I think more than 5,000 Kelvin. So it emits in the visible and ultraviolet region. Earth's temperature, then we get the energy from sunlight, and Earth also emits, but Earth's temperature is much low, about 25 degrees C. So it emits in the infrared region. And we also know the Stephen Boltzmann law, where it says that energy flux is proportional to temperature, fourth power of absolute temperature. So we know that the intensity of sun is actually really high. This is scaled by a factor of 10 to the minus 6. So these are just basic physics, quantum mechanics, and very well known right now. So from this energy balance, we can calculate what should be the energy of Earth, and the mean temperature at Earth's surface should be minus 18 degrees C from this energy balance. So it would be or Earth should be a frozen planet. But there should not be any life. But the observed mean temperature of Earth is actually about plus 15 degrees C. So why is this difference? This is because of the natural greenhouse effect. The energy that Earth is emitting, some of that energy is trapped in the atmosphere, trapped by greenhouse gases such as carbon dioxide, water vapor, and methane. They absorb the terrestrial infrared radiation that's been trapped in their internal vibrational modes. For example, here are some molecular vibrations of water vapor. And that is the reason why our Earth's temperature is much higher. So, do you think that I talked about this Earth's mean temperature, but is it really constant? That's the question. It has been constant for quite long. This figure is from IPCC. This figure is the change in global surface temperature relative to 1850 1900, which is about pre-industrial. So if you look at this plot, for the last 2000 years, almost from 2000 years, Earth's energy was very stable. It was very stable. within the last 100 and 150 years, it has skyrocketed. It is going high like anything. And why this happened? This is because of the extreme use of greenhouse gases such as CO2, methane, NTO. During this period, the concentration of these greenhouse gases also increased, uh, mainly due to anthropogenic activities. Um, and if you look at the concentrations here, well, it's still low in parts per million. Parts per million means 1 parts per 10 to the power 6 molecules. So it's still really low, but it makes a big difference. So here the how much different gases contribute to this warming. Uh, of course, we have carbon dioxide that contribute close to 1 degree centigrade of temperature change. Methane, of course, as I said, there are nitrous oxide, halogenated gases. But we are in my research, we are mainly interested in methane and halogenated gases. So let's now talk about some of my research work from NOAA, which was related to the halogenated gases. We in the past, in the 60s, 70s, chlorofluorocarbons, one of the halogenated compounds, were being regularly used as refrigerants and also in other applications. But it was discovered that they destroy stratospheric ozone layer uh, by a by a catalytic cycle. So in the upper atmosphere, CFCs are photodegraded by UV radiation of sunlight and generate chlorine atom, and this chlorine then is involved in a catalytic cycle and destroy ozone. And from one Cl atom, many molecules of ozone can be destroyed. It is a catalytic cycle, and it was destroying ozone layer, which was observed. Because of that reason, the CFCs were banned by an international agreement known as Montreal Protocol. After CFCs are banned, the new compounds that come to the market are hydrofluorocarbons or HFCs. They do not contain chlorine, so they do not destroy ozone layer, which is good, but they are greenhouse gases. Here I have shown on the red curve is Earth's radiation. Now you see the dips here. Why is that? Because of these natural greenhouse gases, such as this is the absorption of carbon dioxide. This is ozone. But there are some windows which are transparent to infrared. And if you have a new gas which absorbs here, then you will have more energy will be trapped. And in fact, HFCs absorb in this atmospheric window, as you can see. So they are greenhouse gases. They are making our Earth's temperature high. Because of that, in the recent Kigali amendment of the Montreal Protocol, it was decided that HFCs will be phased down. So what are the new compounds now? The new generation refrigerants are hydrofluoroolefins or HFOs and perfluoroolefins or PFOs. So but we want to know, these are new compounds. We don't know a lot about them, so we want to know, are they causing less warming? Are they good for environment? So that's the objective of our work, providing experimentally measured climate metrics of new generation replacement compounds to help in environmental policymaking. I have studied one of these compounds at NOAA, and this is perfluoroheptene, one of the PFOs. And I worked actually with an actual commercial compound. This is a proposed refrigerant, um, and the complexity of this commercial sample is that it is a mixture. It comes as a mixture of different stereoisomers, that is E and Z isomers, cis and trans, as you can think. So 85% is E isomer, 11% is Z isomer, and this mixture, I mean, makes it complex, as you'll see. So the research objective that we had is first measuring a key climate metrics known as global warming potential, or GWP. It is a simple measure of how much warming a compound can cause, and it is expressed in relative terms. it is expressed with respect to CO2. So we consider the GWP value of CO2 is 1, and we want to understand what is in comparison, how much more warming another chemical can cause. And there are two factors that contribute here. One is the radiative efficiency, that is um, how much energy it absorbs. And so it depends. We need to know the infrared spectrum of that. From that, we know how much energy it can trap. So it is done by studying infrared spectra. Second is atmospheric lifetime. So if a chemical survives for long, then it will absorb energy for a long time. So and for that we want to measure OH reaction kinetics. So these two terms, if we know these two terms, then we'll be able to estimate GWP of this compound. And the second is we also want to know atmospheric degradation mechanism. That is, what is going to be the fate of this compound in the atmosphere. Okay, so let's start with spectroscopy, infrared spectroscopy. In this plot, this black curve is the measured infrared absorption spectrum of this compound, this mixture. Now the E and Z isomers, they absorb in pretty same region in infrared. It's difficult to separate them. So we took little help of theory, density functional theory, and these are the theoretically predicted infrared spectra for Z isomer and E isomer, and we compared them with experiment. The plot in gray here is coming from theory, and the black is from experiment. They agree pretty well to each other. Now, from that, we can estimate the radiative efficiency. You can by just estimating the area of under this curve. So the radiative efficiency for the E isomer and Z isomer is 0.12 and 0.19. What does it mean? It does mean that the unit is watt per meter square per parts per billion, which means that if you inject 1 parts per billion of this compound, then the amount of energy it will trap, or amount of energy disruption it will cause, is 0.1 watt per meter square. So we do see there is large infrared absorption cross section in this atmospheric window. So next part is, what is the lifetime? For lifetime, we need to measure the kinetics. To do that, we use a technique known as pulse laser photolysis laser induced fluorescence, or PLPLIF. So first, so we want to study reaction of this compound with hydroxyl radical. Now, hydroxyl radical is not stable, so we need to generate that. We generate that from hydrogen peroxide by doing laser photolysis at 248 nanometer. For that purpose, we use an excimer laser emitting at 248 nanometer. Now, these lasers are pulsed, meaning the 10 hertz laser, so it will keep 10 pulses per second. So this laser generates hydroxyl radical, and then we have a probe laser. This is 282 nanometer. This comes from Nd:arc pumped dye laser. What it does is it excites hydroxyl radical electronically, and then it fluoresces, and we collect that fluorescence light, the laser induced fluorescence, using a photomultiplier tube. So essentially, the intensity of this fluorescence is proportional to the concentration of your hydroxyl radical. Okay, so this is the hydroxyl radical part. And so we flow both this H2O2 and our compound through this cell. And these are other spectroscopic setups. We have a UV spectroscopy setup here, and the FTIR spectroscopy. This is to monitor the concentration of our compound. So let's look at the kinetic results. We do this under the condition of pseudo-first-order reaction condition. This is a bimolecular reaction, but we keep our compound, the heptene, in much excess with respect to OH, so that we can have pseudo-first-order condition, which is easy to handle. And you can see here the pseudo-first-order plots. These are OH intensities at different concentration of our reacting compound. So as you increase the concentration of perchlorheptene, you see the steeper curves. The OH decay is much faster. From that, we can get the pseudo-first order rate constant, which I have plotted here as a function of our compound, which is also known as second order plot. And from the slope of this plot, you can determine the rate constant. It's pretty straightforward, standard kinetics. So the rate constant that we got is 3.9 10 to the power minus 13 centimeter cube molecule inverse second inverse. Um, Now the issue here is that, as I said, again, this is the mixture compound. So this rate constant that we are getting is characteristic of the mixture, not the individual stereoisomers. How can we get that individual reactivities? For that purpose, we use another technique, which is a relative rate technique. In this technique, what we do is we determine the rate constant of our compound with respect to a known compound. We call those references. Like these are the two references we have used. Their rate coefficient is already known. So if we react our compound and the reference both at the same time with hydroxyl radical and see how they degrade with time, then from the relative decay of both compounds from this equation, if we know the rate coefficient for our reference, then we'll know the rate coefficient of our compound. Okay, so the way we do it, again, we use XMR laser photolysis, but we use a different radical generation scheme here. We actually photolyzed ozone in presence of water vapor. And circulated this reaction mixture between this photoreactor and FTIR cell. FTIR is not used for kinetics because it cannot differentiate the stereoisomers well. But what we used for that purpose here is GCMS, gas chromatography mass spectrometry, or we also used ECD detector. This can separate these compounds. As you can see here, this is the E isomer and Z isomer, both are separated along with some other impurities. Okay, let's look at the relative rate data. So here is the data, relative rate plot for E isomer and Z isomer. Clearly, they differ in their reactivities about by a factor of about 1.5. The rate constant for E isomer is 3.6 10 to the power minus 13. For Z, it is 2.2 10 to the power minus 13. So based on that, we can estimate the lifetime. So the E isomer lifetime is 33 days. So it survives about around 33 days. Z isomer is 56 days. So how does it compare with the other method? From PLF, we got 3.9 10 to the minus 13. And from this, if we estimate the rate coefficient for the composite mixture, it will be 3.4 10 to the minus 13. So both methods gave us rate constant which are pretty comparable to each other, which gives us a lot of confidence. Okay, so we have the spectroscopy data and we also have the kinetic data. So now what is the GWP? The GWP is, and we estimate for some amount of time. For example, for 100 years, how much warming it will do. For 100-year time horizon, the GWP values are about 2 and 5. So in comparison to CO2, if we are made same amount, then the warming will be 2 times and 5 times than CO2. So what do you mean by these numbers? Are they large or small? What is that? We can compare it with thing. I probably don't have that information here, but if you look at the typical HFCs, they are in hundreds to even thousands. And this is much lower than that. So it is low by industrial standards. So these are good, and the reason is that the lifetime is much longer, much shorter. If you think about HFCs, their lifetimes are really large, because of that the GWP is high. Okay, so GWP is good, but can you safely say that we can use this compound? The answer is we need to know more details. We need to know the atmospheric degradation mechanism. That is, what is the atmospheric fate of these compounds in the atmosphere? This compound reacts with hydroxyl radical. The hydroxyl radical reacts with this double bond here. There is no hydrogen, so only possible way to uh, react with this double bond. Then it produces a free radical that reacts with oxygen and form peroxy radicals. The peroxy radicals react with nitric oxide or other peroxy radicals to form alkoxy radical, and they degrade to form fluorocarbonyls. So these are the two fluorocarbonyls expected as an atmospheric degradation product, and we did measure those in the infrared spectrum. We did measure these compounds as the reaction product in close to 100% yield. Now, these fluorocarbonyls are of concern because it is known that heterogeneous loss of fluorocarbonyls could form fluorocarboxylic acids. Now, fluorocarboxylic acids are toxic compounds, uh, but how much fluorocarboxylic acid will be formed, we don't know yet. We need to do more measurements for that. But it makes us concerned because although the GWP is low, it could form toxic compounds in the atmosphere. So we need to know the complete atmospheric fate of a compound. That's what uh, I want to say here. Another such example is the atmospheric chemistry of trifluoroacetaldehyde, or CF3CHO. Trifluoroacetaldehyde is a major reaction product from HFCs and also HFOs, and it has been really recently postulated that CF3CHO can photolyze in the atmosphere and form trifluoromethane or fluoroform or HFC23. Now, this would be a big problem because the GWP value of this compound is huge, 12,700. So it has drawn some recent attention of the scientists. If you look at the CF3CHO spectrum, there are basically three degradation channels possible. It can have the radical channels to form these radicals, or the molecular channel, or also known as the roaming pathway. That's what we are interested in. As I said, there is a claim of production of CHF3 from CF3CHO, but we need experimental verification of that. It was detected in the short wavelength, but not in the longer wavelength where I should describe this figure more in more details. This is the UV spectrum of this compound, and the shaded area is the UV light that we get from sunlight in the troposphere. And if you look at the wavelength, it is from about 290 nanometer. The shorter wavelengths are already absorbed by ozone. So in this region, nobody detected this compound from the photochemistry. That's what we want to do. That's the motivation of the study. So and it is also became important because recently when atmospheric chemists, the modelers, modeled it, this the modeled HFC23 emission. The red circles here are the estimates based on atmospheric measurement, and these black squares are based on global industry reporting, recently there is a big mismatch. So something is going wrong. Either there is inaccurate reporting, or these compounds are are actually responsible for that from this chemistry. So we want to understand whether this chemistry is responsible for it or not. So we are one of the first groups that detected CHF3 as a product of actinic photolysis, that is 308 nanometer photolysis of this compound at atmospheric pressure. And to do that, we used a GCMS detection with laser photolysis. And the quantum yield that we measured is 3.3 10 to the power minus 4, which is pretty low. So as I said, previously nobody detected it, but the estimates that were based on the measurement upper limits were in the range of 0.02 to 0.003. So what we actually measured is about 1 to 2 orders of magnitude less than that. And we did measurements at different wavelengths, different pressures. You can get you can draw a Stern-Kolmar plot from that as well. So basically, is it making a difference? No. The contribution from this chemistry, if we plug that into the model, this is contributing really less. So CF3CH photolysis, which initially claimed, but which we from our measurement it is clear that it is not significant atmospheric source of HFC23, which means that there is some other thing going on, and we don't know what's going on right now. Okay, so this is the summary of this part of my talk. We measured the atmospheric lifetime and GWP values of these proposed refrigerants. And the basic takeaway is that we need to know the complete fate of atmospheric fate of these replacement compounds. Okay, let's talk a little bit about my current and future research at University of Rochester. I'll not go into details, but just few glimpses. So here I'm working on atmospheric methane. Methane, as you already know, is the second strongest greenhouse gas after CO2. Its GWP value is 27 for 100-year time horizon. That is, it's 27 times more stronger with respect to CO2 as a greenhouse gas. And the good thing is that its atmospheric lifetime is about 9 years. For CO2, it's 100 to thousands of years. So, which means that if we can decrease the concentration of methane, then within 9 years we should see the effects. That's why methane is a prime target for fast mitigation of warming. But unfortunately, methane is increasing. This is the methane data from NOAA from 1990s. It was increasing. There was a phase between 2000 and 2007 when it was stable and people thought that, oh, it's probably going down, but no, it's again started going up, and the growth rate is even faster in recent years. So the primary question is that, yeah, we know methane is coming both from natural sources as well as anthropogenic sources, but how much are the contribution of these different sources? That is the question. How do we know that? We can measure methane in the atmosphere, but how do we know how much it is coming from natural sources, how much is coming from man-made activities? How do we know that? So a really fascinating field here is the isotope chemistry. Isotope ratios are natural markers for different sources and sinks. So let's take an example of carbon isotopes here. So you know carbon has two major stable isotopes, 12C and 13C. 12C is about 99%, 13C is about 1%. And there is also radioisotope 14C, which is really less. The abundance is really, really low. Now, the thing is that the isotope ratio, that is 12C by 13C, that is different in different sources. Isotope ratio is reported in delta values, which is, it's probably a new term to you. These ratios are really low, so they are, for accuracy, they are reported or measured with respect to a reference. Here the reference is PdB. Um, uh, and it is expressed in terms of per mil, that is in 2000. You see here these numbers are so low that you need to convert it into per mil. So basically, if your 13C content is high, then your delta value will be high. If your 13C value is low, delta value will be low. So if we look at different sources, that is, let's say microbial sources or natural sources, and fossil fuel, which is man-made, if we look at the delta numbers, they are distinctly different. For microbial, it is about -60 per mil. For fossil, it is about -40 per mil. Biomass burning is even higher, -30, -20, something like that. So these isotope ratios are defined in different sources. So from that measurement, we can determine how much is coming from which sources. So if we do a balance of these different sources based on their amounts, the average value of delta C for methane for our atmosphere should be something around -53 per mil. But it is not the case. In atmosphere, the measured delta value is about -47. So it is slightly different. And this difference comes from chemistry. We call it fractionation is removal. Particularly, it is the kinetic isotope effect, because this methane is being degraded by, let's say, hydroxyl radical mainly. Now, hydroxyl radical reacts with these different isotopes at different rates, which is the kinetic isotope effect. Um, because of that, there is a change. Now the problem currently we have is that this is a small ratio, this is a small quantity, 13 CKIOH, and it is uncertain. It's not very well known, and that creates a problem, because what atmospheric modelers do, they take all these numbers and optimize the model. Based on that, they attribute how much methane is coming from different sources. So if we look at the numbers, these are the two currently accepted numbers of 13C KIE 1.0039 by Sorosek and co-workers from MPI Mains, and 1.0054 from Cantrell and co-workers from NCAR. First of all, these are very close numbers. It's probably 0.1% different. What NASA JPL recommended is the Sorosek value 1.0039, but they also made the error bar larger to also accommodate this number as a chance. Now, the small difference make a big difference in source attribution. So if currently the estimate is that the fossil source contribute about 173 teragram per year of methane. If you take this number, if you take the 1.0054 number, it will change the emission from 173 to 131. Big change, about 25% change. Same with for the natural emission, it will change from 374 to 414. So a very small difference in measured KI value translates to a big uncertainty in the source of this to the different sources. So it is highlighted in recent literature. For example, this paper says it is also crucial to determine the KI values of methane sink process more precisely by conducting more laboratory experiments, and that's what we want to do. We need more high confidence KI measurements. One of our projects have been recently funded by NSF, National Science Foundation, where we'll be remeasuring this, and I'm the PI of that project. And this is the we will use a similar photolysis scheme here. We'll do a laser photolysis production of radical. We'll use multiple radical precursors, because the two studies that I said, the one used hydrogen peroxide, another study used ozone as the OH source. So we'll see whether that made any change or not. We'll also do temperature and pressure dependent studies. Particularly, we don't have any measurements at low temperature. and we'll process this in a using spectroscopy method. So it will be a process-free gas measurement. So we're in process of building this state-of-the-art experimental apparatus at the University of Rochester. It will be similar to the NOAA reactor that I worked with. Uh, um, so the plans are to measure these different KIs, 13C KI for OH, also for chlorine. We'll also measure the deuterium kinetic isotope effects, and it will measure the KIs at this large temperature range. So we hope that this new experimental data will likely improve the model estimations of isotopic data and our understanding of atmospheric methane sinks and the overall budget. Okay, now let's talk about some field studies. I talked mostly on laboratory studies. Uh, so let's talk about the radiocarbon now. The radiocarbon 14C carbon is also very useful in this case. Fossil methane is ancient. Carbon is isolated from the atmosphere for millions of years. So you know 14C is radioactive with a half-life of uh, 5,730 years. So there will be no 14C in fossil methane, right? Because they would be already degraded. But if you look at natural sources, there will be 14C content. So if we can measure 14C, then we can get a better idea of how much is coming from which source. To do that, we measure, we collect air samples from different parts of the world. And then this is the schematic of our measurement. Then we do some measurement at our lab at the University of Rochester, do some sample processing, and we send our samples for radiocarbon measurements at Australian nuclear facility at Ansto. So these are the regions where we do the measurements. We have Barrow in Alaska, Mauna Loa, Hawaii, American Samoa. These are the baseline stations, like far from pollutants, so that we can get the base amount of methane. Barbados, Isania, Canary Island, and Bearingham, New Zealand. So we have some in the northern hemisphere, some in the southern hemisphere. And I actually went to Barrow, Alaska last year to install one of our systems. This is the gas manifold that we use. It is automated. We can do sampling from here online, and this is the canister where we fill our air samples. And air is collected from a tower. We took a picture of the NOAA laboratory from that tower. So after collection, we measure these samples at our in our laboratory at University of Rochester. We use a Picaro cavity ring down spectrometer to measure carbon monoxide, methane, carbon dioxide, so greenhouse gases. Then we do measure the stable isotopes, that is 13C and D, using an Aerodyne tildes instrument. Then we do process the sample for radiocarbon measurements. As you probably saw, radiocarbon concentration is really low. So we first have to separate out methane from anything else, CO, CO2. So we have different traps to separate out methane from others. Then we combust methane to CO2, and then we isolate them in the flame seal here. I'll show you a really cool video where. So this is the flame tubes where now the methane sample is trapped, and we send those to ANSTO. This is their accelerator mass spectrometer. This really high power mass spectrometers are required to measure this very small amount of radiocarbons. So this campaign is ongoing. We hope to get some results soon. I think I have a little bit more time. I'll just talk a little bit about past atmosphere. So this is all about present atmosphere. How do we know what was the methane concentration 200 years back? Nobody measured at that time. So one way to measure it, there are airs from that time which are trapped inside ice uh, in Antarctica or Greenland. So if we can extract those air from ice, then we can get a sense of how much methane or other compounds were there 200 years or maybe 1,000 years ago. Uh, so if you look at the data, as I said earlier, methane started increasing during pre-industrial, but we want to know how much is due to fossil and how much is due to due to other sources like agriculture and waste, and we can do it by using isotopes. So we are going to do a campaign next year at Greenland. Will be the site is called Southeast Dome. It is high elevation, about 3,000 meter, very cold, mean annual temperature of minus 21 degrees C, which is good because it preserves the gas as well. Extremely high accumulation rate, 1 meter ice uh, per year. So we'll drill and get ices from about 80 to 230 meter. If we can drill up to 230 meter, then it's equivalent to the year of 1850. Then we'll melt those. We need really large amount of ice. We'll melt those and extract air from there, and then that air will be measured in the laboratory for isotopes. So yeah, that's it. I would like to mention a little bit about the scopes in atmospheric chemistry. It is probably still not a popular field in India. As I said, it's a multidisciplinary research field. As I said, almost anybody from any science discipline can come and contribute. Of course, there are scopes in academics, but there is big scope in industry. For example, the compound that I talked about, the perfluoroheptins, these are proposed refrigerants. So you need to know their chemistry, and of course policy. You can also contribute to the policy. Yeah, I think I'm on time. Yeah, thank you very much for listening, and you can ask your questions now.
Hello.
Yes, yes, I can hear you.
Thank you, sir, very much. Actually, very lucid presentations and nice presentation also. I'm asking a question regarding the taking the sample of air. So I heard that the migratory birds that they are coming so long, and also the many countries, and the feathers of the migratory birds are taken, and also the air sample can be get. How it is fruitful or it is helpful? Actually, I am asking that.
I'm not very aware of that particular application, but if the feathers is taken, there should be some signatures there, but not air. I don't exactly know which signature the scientists collect in that case. There should be some signature.
Okay.
Yes, sir. Good evening, sir. I'm Aratrikson from Kolkata. I study in class 11. So, you have explained very well, sir. I could understand only a bit of 25%, I can say. And, sir, if I want to go deeper into this subject, how should I approach this, and what book should I read, if you just say?
Uh, yeah, you were a class 11 student, so I don't know about any school level textbook, but college level textbook, there is a very popular book that we study, that is called Introduction to Atmospheric Chemistry by Daniel Jacob. That's freely available over internet. You can probably try that, but yeah, for school level there should be some book. I'm not very aware of that, but now, yeah, the online resources are really helpful, so you can
Okay,
search
sir.
those. But yeah, feel free to reach out to me. I can give you some resources.
Thank you so much, sir.
Good evening, sir. Uh, Nice lecture. I have learned the many of things of the basic of atmospheric chemistry and greenhouse gases. So, sir, I have a little question that we know the photochemical smog or oxidizing smog, that is PAN. peroxyacetyl nitrate. So it is very much harmful to the ecosystem for the as it is an oxidizing agent. So in artificially or any laboratory technique, that how the scientist can control the pan formation for the reduction of this oxidizing agent. Sir, any
Okay,
idea
so
about that?
your specific question is, if I understand well, how can you in the laboratory, how can you uh, synthesize pan and control its concentration? Is that right?
Exactly, sir.
Okay, so for pan or peroxyacetyl nitrate, it is important mainly from air quality perspective, not very related to, it's related, climate and air quality are very related, but yeah, pan is really an exciting compound. It's peroxyacetyl nitrate. So if you think about acetone, if you fertilize, you will get a peroxyacetyl radical, and then it reacts with nitrogen dioxide to form peroxyacetyl nitrate. And so what you can do is you can actually in the lab you can generate it in the similar way, the way we did our experiments here. If you take acetone or any other compound like biacetyl, which has this acetyl moiety, and if you fertilize that right wavelength, you can, if you can dissociate the right chemical bond, you will have acetyl radical. Then if you also have nitrogen dioxide in your system, then they will combine to each other to form pan. You can change the concentration or control the concentrations in different ways by changing the concentration of your source gas. That is, if you take acetone, then acetone. If you also you can vary nitrogen dioxide. One thing about pan is that there is it's also the lifetime is dependent on the temperature. It's at high temperature it dissociates. So and that's how it transports nitrogen dioxide. It's a transporting agent of NOx. It goes to the upper troposphere where it's cold, it's more stable. Then it transports to other region, and there it
Yes,
can it can dissociate NOx. So it's a really important compound in the atmosphere, particularly from air quality perspective. And yes, we can do it. We can synthesize it and control it in the laboratory by the ways I mentioned. You can also vary photolysis energy or to control the formation.
okay, sir. Thank you, sir. Thank you.
Uh, Good evening, sir. Thank you for this lecture you have shared with us, and from this I have learned a lot, and understood that I have to learn a lot more. So my question is that you people have collected the air sample from the ice sheets, the older air samples, but sir, through the years of this freezing and all that, the air quality which was earlier was present might get disrupted. No, means the concentration or the quality might get disrupted. So how can we get the original or the proper sample for the research?
So the eyes are buried under. So they do not get the effect of. I mean, the upper layers of ice do get some effect, particularly when there is melting. But if we go to, first of all, we have not collected that. We are this campaign will be next year. But the idea is that we will go deeper. I think what I said will drill up to, let's say, from 80 to 230 meter. So if we go that deep, 80 to 230 meter, at that level, the changing environment outside doesn't make an impact because air cannot diffuse through ices that deep. So that's why that pristine environment of past Earth is preserved there. So that's why we are going to get those. So But of course, if your question is whether after extracting, whether that will make any difference, after extracting, we of getting the ice, we take extreme care. We melt those inside a vacuum chamber so that it's isolated from our current atmosphere. Am I clear, or did you have any distinct question about it?
No, sir. Thank you, sir. Bye.
Good evening, sir. Thank you for your giving lecture. I have a little question. In this lecture, you tell us that you are collecting samples of CH4. Is there a way to control? Is there a way to control the formation of CH4 in atmosphere?
Okay, so good question. We need to understand the different sources. First of all, as I said, natural sources we probably cannot control how much is coming from plants or from soil, but we can definitely control the anthropogenic sources. For example, a big source is fossil fuel, the vehicular emission. If we can limit the use of fossil fuel, of course, we should we can limit methane and other greenhouse gases. And that so far there has been some effort by different countries, but still it is increasing, as you saw. So probably our effort is not good enough as of now, or there is a change in natural emission as well. If natural emission gets higher, we cannot really know about it. And that's a open question right now. Actually, we have been doing a lot of research about this recent increase in atmosphere, whether it is how much is coming from natural and how much is coming from man-made. But yes, our from our part, if we can limit the man-made sources like vehicular emission, industrial emission, then we can definitely limit it. And that's been the ongoing science talks or policy talks throughout the world. How can we do that, or what policies should we adopt to do that?
Okay, sir. Thank you.
Come.
Sir, thank you for your time that you have given to us. My question is, can we find a replacement for CFCs or HFCs before it is too late for our environment?
Yeah, that's a good question. As I said, currently we are the new generation compounds are HFOs, but as you saw, it's much better than HFCs and CFCs, of course, but still it might have harmful effect to our environment. It might be better for our climate, but for overall climate air quality, it might not be the good solution. So yeah, some research is going on that. If you can find the replacement compounds, and yeah, that is an active part of research in this field. And yeah, hopefully scientists will be able to synthesize something. That's what we hope. But these compounds also need to have the right thermochemical properties to act as a refrigerant. So it's tricky.
Thank you, sir.
Sir, as you mentioned that methane is the second largest greenhouse gas, is there any decay process of methane just like CO2 is absorbed by a tree?
Okay, so for methane, the major process is, as I said, hydroxyl radical. That's the major degradation process. But hydroxyl radical is present in the atmosphere naturally also. Its abundance is 10 to the power 6. So that's the main process. There is some a little amount is deposited into soil. That's probably 5%, 10%. But the major part is OH. There has been a lot of talk going on actually. Can we synthetically degrade methane by, for example, if we can have a lot of hydroxyl radicals in the atmosphere? Yeah, we can. But whenever we do part of our nature by introducing synthetic things, we have to be very careful. We have to know first, understand well what could be the other effects or side effects. But there is an active research going on in this case. If we can inject some oxidants or some other materials that can absorb methane, That's an active area, and very active area and very recent area, that if we can somehow destroy methane by reaction or adsorption, then it will be helpful. But we have to know the full picture. We have to know if we do something to our environment synthetically, artificially, what is going to be the overall effect. But it's an active area of research right now.
Yes, am I audible?
Yes, I can hear you.
So I have a personal question that yeah, what is the placement opportunity in this particular field, or what is the career opportunity? Can you explain?
Yeah, I shared my last slide, but I didn't explain a lot. Like every field, you definitely have academic opportunities. Particularly, I think that in India, I think there is not many atmospheric chemists, particularly in the laboratory studies, who work in this area. So definitely, we should have more atmospheric chemists working in atmospheric chemistry in our country. So there should be, but still there is not a lot of opportunities. But I do hope that the opportunity is, in the next few years, the opportunities become more available. But regarding the industry, there is definitely some big opportunities. I don't exactly know about how the condition is in India, but here in US, the chemical companies, they are actively looking at these refrigerants to synthesize chemical which is better for our climate. So if you are, let's say, synthetic chemist, you can definitely contribute to that. And if you are a physical chemist like me, then you can characterize those compounds, and assess whether that's good for our climate and environment or not. So there are definitely a lot of industrial opportunities here. And the other thing that I didn't mention well is policy. Uh, the science policy is really important in this respect, and all of these things came up during our conversation, that can we make a policy to reduce these emissions? Yes, but that involves not only science, but also government, etc. So you can also, it's probably not yet very common, but in India, but if you can also be a policy person in this area. So I think there are scopes. I'm not in India right now, so I don't have a sense of how much exactly the scope in India. But here, at least in US, there are a lot of scopes. Another field that I didn't describe well is atmospheric modeling, because I do not do modeling. But atmospheric modelers are also they're uh, uh, th- their job opportunities are really high, because they can model at what, if you do the model the future scenarios. So they make valuable impact. So in my opinion, there are opportunities not only in academics, but also in industry, as well as in policy. But um, yeah, but hopefully in India also, these different opportunities will be more available in future. I hope.
Sir, can I ask you a question?
Yes.
Sir, I'm a teacher of humanities and I could not understand 90% of your lecture. But what I have understood that our children, if they are interested to go for these studies, how can we inspire them for this? Because as just now you told that there are no such opportunities right now in India. As my son is also there in this seminar and he's listening to you, and he only asked for this deeper knowledge, and you have mentioned a book, sir, suggested a book. So, as a teacher, as a mother, I just wanted to know a suggestion I wanted from you, that how can we inspire our children for this awareness, this topic, because it is very difficult topic, and since it is not that much popular in India, how can we inspire children and can add it in the curriculum? What do you suggest, sir, as a scientist? Or should we add it in the curriculum of CBSE and other boards so that the children can learn it from at an early age? That is my question, sir.
Yeah, definitely. These things should be added into the curriculum. I'm not very well aware of recent curriculum. Also, I do not say, I didn't say that there is no opportunity. There are opportunities. I know some laboratories at least in the undergraduate and postgraduate level. I know some laboratories who work in atmospheric chemistry. For example, there is a group at Aizen Mohali who they do a lot of measurements. There is a group at IIT Madras. They do laboratory studies. But what I am saying is that there should be more people who should be working on this important topic. For example, we see a lot of biophysicists, but these environmental scientists science should also be given preference. So regarding the curriculum, yes. First of all, I don't know about current course details, but what I recall from my time when I was a student of there was no such course of atmospheric chemistry. It definitely should be included in bachelor's and master's level in chemistry. uh, and uh, and uh, and in school level, I think they probably get some idea about like greenhouse gases and air pollutants, but there should be more in more structured way, like what are the actual molecular mechanisms, so of let's say light absorption or infrared absorption, etc. So yeah, I think that from the perspective of, I mean, who are in charge of creating these curriculums, I think we can the educators, they can talk to them in more details and ask them, uh, I mean, convince them that this is important. This is not only important just from the perspective of science, but also from our country, because India particularly is air pollution. We are not doing good. So if the educators can convince the people who are in charge of the maintaining the syllabuses and curriculums, then that will be then everybody will get an opportunity to learn about these things. So I think that should be done, if it has not done already, because as I said, I don't know about the current syllabuses and courses. What I said is from 10-20 years back when I was a student.
Thank you so much, sir. Thank you.
Thank you so much to Dr. Aparajeo Chattopadhyay. Now I formally am giving the vote of thanks. So it is my good privilege. Am I audible?
Yes.
It is my proud privilege on behalf of the organizing committee, Ramakrishna Mission Vidya Mandira, to propose the vote of thanks for today's enlightening seminar on atmospheric chemistry of greenhouse gases. So first and foremost, I extend our heartfelt gratitude to our esteemed speaker, Dr. Aparajeo Chattopadhyay, a distinguished scientist from the USA. Your lucid explanations, deep insights, and thought-provoking analyses have not only enriched our understanding of the complex chemistry of greenhouse gases, but have also inspired us to give more critically about the climate changes and its mitigation. I also take the opportunity to thank our respected dignitaries and our principal Maharaj, who has given us this opportunity to conduct the seminar. A sincere thanks to the placement and career counseling cell technical staff, support staff who are present in the seminar, and volunteers for the meticulous planning and smooth coordination, without which this seminar would not have been possible. Finally, I am grateful to all the participants for your keen interest, active engagement, and thoughtful questions which made today's session truly interactive and impactful. Let us carry forward the knowledge we have gained today and work together towards a sustainable and environmentally conscious future. Thank you all once again. Thank you to our resource person, and thank you again all. We now conclude the session.
I also want to thank you everybody, particularly Jeet Maharaj, who is my dear friend, and also everybody, all the participants here, all the students, and of course the President Maharaj and all of these members of Ramakrishna Mission. Thank you very much.
Okay, so আমরা এক্সপেক্ট করবো যে আমরা ডক্টর অপরাজিত চট্টোপাধ্যায়কে আমরা we can expect him in the near future also.
Sure.
Yes.
It will be my great privilege. Yeah.
Yes. Thank you so much. Thank you.
Bye.